All right. Hi everyone. Welcome to one of the first videos that I'm ever going to record on YouTube. And I think this channel is going to be about data analytics, data related algorithms, different things that I have learned working in this industry. And yeah, the main idea is to share these with you guys, get your thoughts, and basically to learn and develop on my own skills as well, right? Cool. So to start with, I think the first lecture that we are going to cover today is going to be regarding linear regression and finding the best transformations associated with linear regressions that we have, right? Now, for the people who are slightly new to the channel, to talk about linear regression, I think I'll just write it as linear regression. What linear regression basically helps us to do is it helps us to quantify a relationship between two variables in a way. One of the variable is commonly referred to as Y, which is our sales, equivalent to sales in terms of business context. And sales is something that is going to be dependent on the multiple other factors, right? And across different industries, what we see is different companies, be it pharmaceuticals, be it any sort of industry, they do some sort of promotion to influence sales, right? So that is like one of the final goals is to maximize the sales that we have. And what linear regression helps in this business context is it basically helps quantify this relationship of sales across the different promotional tactics that we might have deployed, right? We could have TV ads, we could use Facebook as a means of promotions, we could deploy banners, and so on and so forth, right? So what linear regression basically what helps us determine is this relationship, and it will basically help us in quantifying this relationship that we're going to get here, right? So what you can imagine it to finally provide us is a equation which would be sort of sales as S is dependent on, for example, my tactic one would be x1 plus x2 plus x3 plus if you remember the linear equation that we used to study in our elementary school, and we also have some part of it that is sometimes referred to as an intercept. Now this is one of the target or the final equation that we'll aim for in linear regression, and this is what is really important to the business as well. Now why am I giving the business context here again and again? Because what the business knows is the amount of money they have spent on each of the promotional tactic, right? They know the dollar value they spend on tactic one. Similarly, they know the amount of money. The color is not coming out to be fine, but that is fine. So they know the amount of money that they have spent on each of the promotional tactic that we have here, right? But after a year, when they have to revisit their brand plans or their portfolios for the next year when they are making those adjustments, it is really important for them to understand how has this promotional tactic performed, right? So it could be that the target audiences are more susceptible to promotions using these two tactics, and these two tactics are working fine. So what they would want to do in future is they would want to reduce investment here and increase investments in these channels. So that is like a big idea of why we use linear regression in different business analysis that we do, and I hope that makes sense. Cool. So what we are going to focus on today is finding out the best transformations, and I'll get into why we are looking into it today. But for now, I hope the idea of linear regression is clear. Why are we doing that? Doing it here in terms of a business context. All right. Bit new to this tool. Yeah, I think the delete button would do it. Cool. All right. Now, why are we transforming here, right? So what we are doing over here, we are performing a linear regression. And I'm not going to get too deep into the mathematical granularity behind the same, but one of the thing or one of the basic assumption as you can get from the name of the algorithm itself is that there has to be a linear relationship between the x and our y, right? So that is the represented in the form of the equation that I finally came up with, right? That y is dependent on x1 plus x2 plus c, you can say, right? So there has to be this linear relationship between the two. But in terms of business, what we usually do see here is that we don't. see this relationship or linearity coming out in the raw data that we get for any sort of analysis. And that is again really important. And why is that so, right? Why in the real world data we do not see this linear relationship coming out? So how I usually try to think about the same is, uh, for example, let us say there is a store S. Yeah, there's a store in a city, and we have hired a person who goes to the store and talks about the product. For example, say we are selling a new form of electronic device that helps us record the songs that we have. So, a recording system, you can say, right? So, we have a recording system. We have hired a person who goes to the store and talks about the new product that we have. This is kind of a promotion that we are doing here, promoting our product in this store. And based on this promotion, what the store does is it places an annual order of, say, for example, 100 units. Now, from a business context, anybody would want to know if I can influence this final units that are being sold here, right? So some people would could say or could argue that if I increase my promotion, the sales should also increase. That is true. It could increase, it may not increase, that we definitely can't know. But the underlying hypothesis that we would have here is how would the increase in the promotion here affect the sales that are happening here? Right. And based on the linearity assumption, what we say is there is a linear relationship. So if this increases, the sales should also increase side by side, right? But that is something that never happens in the real world data, right? If you keep on increasing a promotion, if you meet or go to the store, say 1,000 times in a year, you cannot expect your sales to go 10x, right? That's not going to happen. So the basic idea is that we always have a diminishing returns if I talk about the x variables that we have and the y variables that we have. So even if the x increases, the rate at which y was increasing it reduces. Something sort of this, right? So every more effort that you increase, the amount of y that is increasing is slowly going down. So this is a really important thing in terms of business that we usually see across different analysis. That is the diminishing returns. This is something that is observed in our data as well. So that is why, again, the data that we get from in terms of raw variable is not always following this linearity assumption, and that is where we apply these different kind of transformations. So we're going to talk about what these transformations are and how do we apply them. Now, to talk about transformations, what do I mean by transformations? To quickly talk about it, it's basically we get a raw variable that is x, right? And we do not, while running those models or while quantifying this relationship, we do not keep this x variable as is. We create a functional form of it. We apply a function which could be, we could apply different functions here, and we model on this. So the final equation would become y equals to function of x plus c. So today we are focusing on this function, on how could we find these functions, what are common functions that are typically used, and yeah, we'll see more about it today. Cool. So what I have done here is I have, again, I think this is quite basic. I have created some sort of random data with the X and sales. We can ignore this for now. I can switch to the mouse and scroll a bit down, and I think these all the steps that you see here are again creating those X and Y variables for this illustration purposes, right? What I would do over here is I would quickly shift focus to this chart that we have, and then what we can do is we can quickly go through the code and I can give you a high level rundown of the code itself. Cool. So I think I need to scroll a bit down as well. All right, I think this would be fine. So what we have in the X variable is the promotion that we have done, the X variable itself, and on the Y, what we have is our sales, right? So this is sales. Now over here, the first thing on the chart that you can see is the original data that is represented in the form of these grayish, or I'm not sure the exact color, but this grayish bluish shade kind of points or dots that you see, right? So again, the thing we were discussing, right? Uh, What we see is when you're increasing your X, the grayish points are following kind of a diminishing return pattern over here, right? So we have to account for this as well. And I think I have few of the results here handy with me. So especially if we focus on the red points that we have on this chart, right? So what do these red points represent? These red points are representing the output of the regression when you're not applying any kind of transformations on the variable. So the red line, if I talk about, this is really horrible. Yeah, so this red line, what this represents is this represents y equals to x plus c in a way. We only have one variable. So this is what this represents. Cool. Now the thing is, as this is a linear equation and did not apply any transformations, what we see is the predictions that we are making here, they are quite far away from the actual data that there is, right? So it's not explaining the data very well. So what we do over here is, especially from a business point of view, what we do is we apply this transformation usually. And this is again, as the log curve is something that is kind of diminishing in nature, applying this transformation on the data fits the data very well. And that is what you see in this bluish shade line and the greenish shade line as well. To keep it simple, in the first case, what you guys can say is we are applying this log of 1 plus x transformation. That's it. So applying a log transformation on the data. First doubt that we might have here is why are we adding this one? Again, this is just from the mathematics point of view. We would not want the value to be anywhere less than 0, right? Because that would give those functional errors. Log would not work there, correct? All right. So I hope the raw variable or the raw line is clear here, right? If you directly plot a equation or run a model here, this is the prediction that we get. And what you can see over here, the prediction is not good, right? We have these errors, so many points here, so many points here, which are quite far away from the data. And we are not capturing the data in the right way. The R square, which you can consider as a score, is 74%, but as you can see in the above two models, it has improved to 86, 87 percentages after applying transformations. So in a way, without transformation, the model was not working as well. Cool. So again, to talk about the basic transformation, that is the first one, log of 1 plus x. What we see over here is the R square has improved. And again, this is coming or stemming from the same business understanding, right? That we have a diminishing returns when we improve or increase our promotions here. So the green line you can see is kind of following the log curve only because the functional form over here that we have applied is log of 1 plus x. So we are modeling sales against this. Y is equals to this plus a constant output. So this is the functional form that we are incorporating here. My phone is ringing. These guys don't know I'm recording the video for the first time. All right, cool. So I hope this curves gives you an understanding of how the transformations are improving here, right? So log transformation is improving the result. But the next question is, again, if you look at the transformation, it's not very straightforward, right? Because the actual transformation could be log of 1 plus ax, where we could have different values of a here. And how do we find the most optimal value for a? That is something we are solving for in one of the functions that I've just written above. I think I can quickly give you guys a walkthrough of the code above, and I think that would help here. Cool. So yeah, getting back to the pin. All right, I need to scroll a bit down as well. Where are you finding it? Yeah, this is the objective function that we've written. Perfect. Cool. So the idea what that we're performing in this function, I think these two chunks are the one that we are using over here. This one, the result, and main function is this one, right? So by applying transformation, what am I changing? I'm changing only my x variable, right? It is changing as log of 1 plus ax. So when I change my a, the x functional form or one of the x variable is changing, right? Now, for my modeling, I'm not sure which x value I need to take. So I simply run a regression, simply run a search here in a way you could say, or optimization here to give me the value of a for which I'm getting the maximum R square. R square has to be maximized in a way. So that is the simple function that I have created here. So if I quickly delete it, if you look at the objective function, it takes x, the parameter that we just discussed, the x variable, the y variable. So what it is doing over here is it's creating the transformed variable that is log of 1 plus a into x. So this is another way of representing the same. We fit a linear regression model over here and we return the minus of r square. So if I want to maximize r square, what would I need to do if I add minus to both sides? I would have to minimize the negative of r square. So that is what we'll do over here. We'll minimize it. So that's, I hope that makes sense. Cool. So this is one of the function that returns the r square. It calculates the r squares at different values, what we provide here. And different values of these are provided using this minimize scalar function, where we have given our function. We have given the different values where we want to check a at, and we have given our x and y variable as well. It is a bounded function, so it's going to check between these ranges itself. So that is the kind of optimization that will do. So again, it's like some mathematical sort of back-end calculations that are going to happen. It's going to check for all of these and return the a value for which r square is maximum. Right? So it's going to give me one of the best a's that we have. And so in a way, what would I finally be left with? I'll have first equation, that is y equals to x plus c. The second equation, where y equals to ln 1 plus x plus c. And lastly, I'll have the best fit equation with the best fit value of a as well, which is, I'll just write it for a dash, which is the optimized value of a plus c. So we notice that this is not working very well, right? We have big question marks coming into this equation. This works really well, but we're trying to focus on if we could improve this further, right? So again, I think it's time to delete all this yellow color. I'll have to change this color from the next video onwards, I guess. Cool. So yeah, and that is what we see over here, right? The green one is the equation that gave us an R square of 85 point, almost 86%, and we do notice some improvement happening here. Although in this case, the improvement is not too much, but as you see, right, we have that optimal A, and finding that optimal A would give me the best kind of transformations that we can have here. So this is the idea that I wanted to cover in this lecture team. I'm saying team, but the audience whoever watches this video. So this is how we can find and optimize our transformations for linear regression. This is just the log transformations that we touch based on this video. But we could have different other kind of transformations using the power functions. We could use negative exponential functions as well, yeah, neg x functions, square roots, so on and so forth. So we have these different kind of transformations. I'll have another subsequent video where I'll first talk about the different kind of transformations that we typically that we have. What are the do's? What are the advantages of them? So ticks, crosses, in a way, which kind of transformation you should use when. I'll research about that and we can talk about that in the next sections. But in a way, applying transformations help improve the linearity of the models, right? And even we could further improve the transformations, right? By playing around the hyperparameters that we have. So I think this was what I wanted to cover in today's video. So yeah, please feel free to post your doubts on the comment sections of the video. I think this is one of the first video that I will be posting. So yeah, any views, any comments that I get will be really really helpful. So yeah, I'll end this video now. Thank you.